Hello, good afternoon, guys. Please type in your name and let me know who all are there. Hello, Shreyash. Sanjana, hi. Good afternoon. Okay, guys, so last class we were discussing some problems of thermodynamics, like if you remember. So, like I said, few questions were left in this particular chapter. So, I'm just going to cover those questions first, and then we'll solve some questions of hydrocarbon with GOC, right? So, GOC and hydrocarbon also will solve some questions in this session. But first, we finish few questions of thermodynamics, which is left in the last class. Okay. So, this is the first question that you can see on your screen. Okay. Try this and tell me the answer. Tell me the answer of this question. Assertion is spontaneous process is an irreversible process and may be reversed by some external agency. The reason is decrease in enthalpy is a contributory factor for spontaneity. Take an example of spontaneous process and then try to find out the answer of this question. Hello, Ramcharan. Take an example of spontaneous process, then you'll probably uh, able to solve this question. What happens in a spontaneous process that you first try to understand with an example. Ramcharan is getting option A. Tell me, guys, answer. C. Shreyas is getting B. Sanjana is getting D. Okay. So some of you are getting D, B, and C. All the options probably I'm getting now. You see, in this question, like the question is related to a spontaneous process. Okay. So what is an spontaneous process, first of all? So you see, if you take an example of like a spontaneous process, we can take many examples. So suppose I am taking evaporation of water. Evaporation of water is an spontaneous process. Okay. However, boiling is not an spontaneous process. So what happens in evaporation of water? Like water converts into, or we can say liquid converts into vapor, right? Can we reverse this process? This process can we reverse? Yes, we can reverse. How? We can easily reverse this process by applying pressure. By applying pressure, right? So obviously, spontaneous process can be reversed by some external agency, right? So obviously, assertion A is right. Okay, decrease in enthalpy is a contributory factor for spontaneity. Obviously, you see, if I take the another example of this spontaneous process, let me take one more example. That is flow of water down the hill, right? So what happens in this process? water is flowing from the hill, right, to the bottom. So obviously the potential energy is decreasing, right? So what we can say, this process is accompanied by decrease in energy. Decrease in energy, right? So we can reverse the process, yes, and the energy also decreases here. That is what we have here, decrease in enthalpy, right? So obviously assertion and reason both are correct. Okay, so A and R are true, A and R are true, right? So we can have the answer either A or B, correct? Now the other part of this, of these options are what? R is the correct explanation of A. Okay, so here you see what happens. This and this is not at all related. If decrease in energy takes place, this has nothing to do with the irreversibility nature of or irreversible nature of a spontaneous process, right? So since both statements are true, SS and origin both are true, but R is not the correct explanation of A. Okay, so this is what answer of this question will be, option B, right? So simply what we can say, spontaneous process is accompanied by decrease in energy and increase in randomness also. So the bottom line which you have to keep in mind, that spontaneous processes are accompanied by decrease in energy or enthalpy and increase in entropy, randomness. How we know this entropy increases? Because when liquid converts into vapor, right? So obviously this is more this has more randomness. Okay, that's why we say, see what happens in this. What is this reason? Decrease in enthalpy is a contributory factor of spontaneity. See, spontaneous process we have discussed already, right? So when decrease in enthalpy takes place, you can also understand this in a different way. I have explained this with the help of an example. But when decrease in enthalpy takes place, what happens? It means the process is going from high energy to low energy, high energy to low energy, decrease in enthalpy. And low energy is what? Is more stable state, right? So if you try to understand the concept of any processes, they are either going towards the more stable state or more randomness. Okay, so in the second state, decrease in enthalpy is a contributory factor of spontaneity, right? So fine, since decrease in enthalpy takes place, so the energy will be low over here and hence the stability will be more, and that's why it is spontaneous in nature. Any process from high to low energy, because of more stability, it will be spontaneous, right? So since spontaneity, decrease in enthalpy takes place, so it is a contributory factor, correct? And obviously R is not the correct explanation of A. Clear? Understood? But for delta G to be negative, enthalpy can increase or decrease, so that does not affect the spontaneity. It depends on temperature also. Ramcharan, temperature you cannot neglect here. See, the only thing you don't know, when you consider delta G over here, right? Then you have to consider the temperature also, because it is temperature dependent term. right? Since we haven't discussed about temperature over here, so simply you can understand by two simple methods, two simple things you can think over here, right? Any process from high to low energy going towards more stability, and when the process is towards stable state, right, the nature of this process will be what? It can be spontaneous, right? Most of the time it is spontaneous only. Second thing is what? If it's like you see this example, it is going towards higher energy state, liquid to vapor. You have to provide energy into it. It is an endothermic process. But since energy is increasing here, but at the same time, entropy is also increasing. So randomness is also increasing. So that's why we say the process always goes towards more stable state, which is the lower energy state, or more randomness. Is it clear? If enthalpy increase or decrease is a factor over here, it depends on temperature and the nature of the process, whether it is exothermic or endothermic. Clear? Understood, all of you? Right. Next question you see. Solve this. Done? Guys, this K is the equilibrium constant. Okay, now first of all, you try to write down the relation of equilibrium constant, that is log of equilibrium constant log K, with temperature. Try to establish the relation first, then you can compare and get the term. Got it? Okay, I'll do this. You see, for an isomerization reaction of A gives B, the temperature dependence of equilibrium constant is given by this. Okay, the relation is given. We have to find out delta S. Okay, so first of all, we know the value of this, or the expression of this free energy with the reaction quotient. What is that? Delta G is equals to delta G naught plus 2.303 RT log Q, right? So at equilibrium, what happens? At equilibrium, delta G is equals to 0. You know this? So delta G naught is equals to minus 2.303 RT log Q, which we can also write minus RT log E base Q or ln Q. Okay, so this is the condition at equilibrium. Now, we know the relation of delta H and entropy. Since entropy we have to find out, so we can write down again delta G naught is equals to delta H naught minus T delta S naught, right? Delta G naught is nothing but this, so that I'll substitute over here. It becomes RT ln Q is equals to delta H naught minus T delta S naught. Oh, sorry, one thing I missed here. You see, at equilibrium, right? Reaction quotient also becomes equilibrium constant K, right? That also I'll substitute here. So this Q is nothing but K here. This Q is nothing but K here. Here also it should be K, equilibrium constant. Okay. So now ln K is equals to delta S naught divided by R minus delta H naught divided by R into 1 by T. So now you can easily compare this equation and this equation. You will get delta S naught divided by R is equals to 4, and delta H naught divided by R is equals to 2000. So then delta S naught will be what? 4R. So answer will be option A. Is it clear? Understood, guys? See, when I got the expression of ln k, Shreyash, okay, why I have taken ln k? Right, because you see the question, the left hand side in the given equation, in the question, it is ln k itself. Okay, so I'll try to write down the expression of ln k in terms of temperature. Okay, so I'll try to write down the expression of this. Similar expression I'll try to write down here. Okay, so when I get this ln k is equals to this, so this equation you see, this equation you can compare with the equation given in this equation, right? So you see this equation here, it is ln k is equals to 4, and here we have ln k is equals to delta S naught by R. Delta S naught by R is equals to this 4 here, right? That is what I have written here, and we'll get the value delta S naught. Understood, Shreyas? Okay, next question you see. This is on Carnot engine. Okay, 35th one, all of you are getting C. 533.3 Kelvin. Yeah, it's the direct formula. Okay, efficiency of Carnot engine. I'll not solve this. I'll just write down the formula here. Efficiency eta is equals to T2 minus T1 divided by T2. Okay, so everything is given 0.25. T2 you have to find out. T1 is given 400. You can substitute and get the answer. Okay, so answer will be the temperature T2 is equals to T, which is nothing but 533.3 Kelvin. Direct formula we have here. Next question you see, this one. Question number 36. Vaishnavi is getting A. Okay. So the formula here we use is delta G is equals to delta H minus T delta S. So delta G is 0 at equilibrium. That is the only thing you have to know to solve this question. So T is equals to delta H divided by delta S. Both values are given in the question. And once you solve this, you will get 400 Kelvin. Okay. Next question you see. What is the answer for this question? Tell me fast. I'll move on then. 37. What is the answer? 37 is B, right? Just now I have written the expression, so it's B only. Minus RT ln Kp you can write, or you can write minus 2.303 RT log Kp. Okay, so option B is correct. Next one you see, this one. All of you are getting C. Okay. So if the question is, we have delta H and delta S values given. Okay. And we have to find out the temperature at which the reaction would not be spontaneous. Okay. So for non-spontaneous reaction, what we can write that delta G should be greater than 0. This is what the condition we have. And we know the relation of delta G and this delta H minus T delta S. So in this expression, if we apply the condition of non-spontaneous process, we will get delta H minus T delta S should be greater than 0, which is nothing but temperature is less than delta H by delta S. Okay. When you substitute all these value here, you will get the answer, and the correct answer is option C only. So all of you have got the right answer. Next one you see. What about this match the column? Saundanya, Ramcharan, Shreyas and Sanjana, all of you are getting A. Tell me others, what is the answer? Entropy of vaporization is always positive, decrease lowest entropy delta H of vapor by TB. Correct. So obviously, option A for this A, this fourth one is correct, right? Because we know this is the formula we have. Del change in entropy when vaporization is there is equals to the enthalpy of vaporization divided by the temperature at which the liquid boils. That is the boiling point of the liquid. Okay. And this value is always positive also, right? So A is nothing but 2 and 4. See, if you see all the option, okay, all of you are very sure that A must be 4, right? So this, if you are sure with this, okay, when you see the option, you can easily eliminate option B and option C. So in match the column, you always try to use these tricks, okay? If you have one or two information, with that you can easily eliminate few options, okay? Now we are left with, or we are, no, if you're confused with 2 and third, then we can see the next option, K for a spontaneous process. When the process is spontaneous, then equilibrium constant is what? It is always positive, right? You see, for B is 2, B is 2. So that is also not, we have to look into that, okay? Option C you see, crystalline crystalline solid state can have what?
crystalline solid state, right? It is the ordered arrangement we have. Crystalline substance are will have the ordered arrangement. Okay, so it always have the lowest entropy, because the confusion is what, whether it is 3 or 1, right? So crystalline solid state decreases what, it does not make any sense. Okay, so hence this C can be 3 also, which is the lowest entropy. So hence the answer will be option A, right? So all of you have got the right answer. I think yes, all of you have got A only. Next question, you see. Solve this one. This question is a bit different. Hello. 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 Okay, so Visist is getting D, Ramcharan D, and like all of you are getting D. Okay, so answer is 97%. That is D only. Okay, so all of you are getting the right answer. Okay,
You see this question, in a fuel cell, the reaction is given. The standard enthalpy of formation of all these things are given. So first of all, we can find out the del G for the reaction. Okay. So the reaction change in Gibbs free energy for the reaction will be what? Del G of formation of CO2 plus del G of formation of H2O. Right? Since 2 moles are there, so into 2. This minus del G of formation of CH3OH plus 3 by 2 del G of formation of O2. This is the expression we have. Now all the values are given. You have to substitute this value and you have to find out the del G for the reaction. Okay. So once you solve this, the del G for this reaction, you will get 702, 702.6. Okay, I have done this calculation, so I'm giving you the direct value over here. 702.6. Now, the percentage efficiency of the fuel cell you have to find out. So percentage efficiency will be what? It is the energy that has been, utilized, which is 702.6 divided by the enthalpy of the reaction, which is given 726 into 100. Right? When you solve this, you will get 97%. Okay, hence the answer will be option D. Right? Next question you see. Solve this one. Okay, Visist is getting B. Vaishnavi, Sanjana, B. Saundarya, B. Okay. So all of you have got the right answer. See, this is also formula based question. Log Kc we have to find out. Del H and del S for the reaction is given. Right? So we know the relation of delta G naught is equals to delta H naught minus T delta S naught. Since log Kc we have to find out, so we'll substitute this del G in terms of Kc, right? And the expression will be what? Minus 2.303 RT log of Kc is equals to delta H naught minus T delta S naught. Okay, so all these things, you see, the value of delta H is given, delta S also given, temperature also given, RT we know, so log Kc we can find out directly. So when you solve this expression here, again you will get log Kc is equals to 10. So that's the answer, option B. Okay, you see the few questions on this relation, delta G is equals to this relation and this relation. There are they ask many questions on these two relations. Okay, so you must remember these two relations in the for the exam. Next question, you see this one. Tell me the value. Set of thermodynamic parameters is given. What is the correct value? Liquid is converting into gas. Why it is D? Option D. Okay, delta S is positive, fine, because liquid is converting into gas. Why delta G is negative? Is it negative delta G? Tell me. Okay, Vaishnavi and Sandhya is getting A. Why delta G is 0? Tell me, Vaishnavi, Sandhya. And why it is negative? Tell me others. Ramcharan, Shreya, Sanjana, Patnesh. Yeah, correct, Vaishnavi. No, actually, you see, this is what happens. I think all of you are sure with positive entropy. Okay, that we are not discussing, right? Because liquid is converting into gas, so delta S is must be positive. See what happens, you have water here, H2O, and you are heating this water at 100 degrees Celsius, and you'll get water liquid we have here, and here you'll get water, gas or vapor, whatever you say, 100 degrees Celsius, right? So now at this temperature, we know the liquid and gas both exist in equilibrium at 100 degrees Celsius, which is nothing but 373 Kelvin, right? So at this temperature, both liquid and gas exist. So we have an equilibrium over here. So that's why delta G is 0 at equilibrium. right? We are supplying heat into it, then only the temperature will increase. The process is not spontaneous then. See, this is the process, right? It is not a reversible process. It is not written here, but it is a process. We are heating this water. We'll get gas at 370. Now, at this state, what happens? We'll have liquid also and gas also. So, at that stage, what happens? That's the question is. Understood? Ramcharan, got it? No, for any kind of phase change, we cannot say Soundarya. See, the process must be at equilibrium. Then only we can say delta G is equals to zero, right? Phase change, this phase change takes place at higher temperature also. There will also be conversion of liquid into gas or any kind of conversion is there. But since temperature is not 100 degrees Celsius, so there that is not at equilibrium, right? So equilibrium thing in case of water and vapor, water vapor and water liquid that you have, it always exists at 100 degrees Celsius only. That's why delta G is zero. For any other liquid, if it's vapor and liquid will be at equilibrium at 200 degrees Celsius, then at 200 degrees Celsius only delta G will be zero. Right? It depends on what temperature we have. Otherwise, we cannot say. Right? Point is delta G is always zero at equilibrium. That is what you have to keep in mind. And since in case of water, we know the vapor and liquid both exist at 100 degrees Celsius, it means we have an equilibrium over here. And that's why delta G is zero. I hope it is clear now. This one, all of you are getting D. Okay, so D is the right answer. Since the process is spontaneous, so reaction is going into forward direction. Okay, and forward direction reaction is only possible. Forward reaction is possible. What happened? Just a second. I think some. Okay. Okay, so forward reaction is possible when K equilibrium is greater than 1. Okay, spontaneous, so delta G should be less than 0, negative, right? And we also know delta G is equals to minus NF E naught cell, right? For this to be negative, this E naught cell must be positive greater than 0, right? Hence option D is right. Okay, so all of you have got this already. So I'll move on to the next question. Okay, now this is now we are discussing questions on uh, GOC and hydrocarbon. Okay, so this is the first question. You have to find out the acidic order of these. Ramcharan is getting C, Saundarya A, C, D, Sanjana is getting. Okay, you see, this is experimental. This question or the order is based on the experimental value, that is Ka or pKb or pKa value. Okay, so first of all, you see, if we compare thiols and alcohol. Okay, so since the alcohol general formula, if I write, it is ROH. Thiol general formula is RSH. Okay, so generally what happens, thiols are stronger acid than alcohols. First of all, this you must remember, thiols are stronger acid than alcohol, because oxygen being more electronegative, it is very difficult to lose H plus over here. comparatively with comparison to this RSH. Okay, so thiols are the stronger acid than alcohol. So obviously, if you see the option, the first is the most acidic compound we have here, right? Now, if you compare the acidity of alcohol and water, okay, so in alcohol and water, this value you have to memorize. Okay, the value of methanol. See, generally what happens, I'll just write down this value also over here. Generally, alcohol are alcohols are weaker acid than water. Weaker acid than water. But we have one exception here. And that exception is what? Exception is methanol. So what we can say, except methanol, all alcohols are weaker acid than water. Okay, except methanol, all alcohols are weaker acid than water. Okay, so methanol, the value of the pKa value, if I say for methanol, the pKa value is 15.5, and on this basis only we are saying this. That's why I said it is a bit experimental. For water, the pKa value is slightly higher than methanol, 15.7. You see, the difference is not that much. Okay, and we know as pKa value increases, acidity decreases, correct? So that's why the order of acidity will be methanol is CH3OH is more acidic than water, than any other alcohol. So order will be, in the last we have ethyl alcohol, ETOH, and before this we have thiol, which is nothing but CH3SH. So order will be first, and then second, and then third, and fourth. So first option is correct here. Okay, so this value or this order depends upon the pKa value. That's why I said it is a bit theoretical. Okay, always remember thiols are more acidic than alcohol. Alcohol and water, if you are comparing, so methanol is more acidic than water, and all other alcohol are weaker acid than water. Clear? Can we move on? Next question. Nucleophilicity.
Basically, you have to find out which one is a better nucleophile. All of you are getting A. What about first and second? First and second, if you compare, then what happens? Okay, you see, the answer for this question is option C. The correct answer is option C. Why, I'll tell you. First of all, we have discussed just now the acidic order. We have discussed just now. Okay. And that is maximum for CH3SH. Then we have CH3OH. After this, we have H2O. And then we have ETOH. Right? So if the acidity order is this, then the conjugate base of this will be CH3S minus CH3O minus OH minus and then ETO minus. So more strong acid, its conjugate base is what? Weak but stable, right? For a strong acid, its conjugate base is weak and but stable, right? So if you write down the basicity order of all these, basicity order, it will be reverse like this. Okay, basicity order will be this. Now you see the next thing here. There is a one rule for nucleophilicity, and the rule is what I'll just write down here. That when nucleophilic center is different, you all write down this rule. When nucleophilic center is different, okay, and they belongs to the same group, they belongs to the same group, then their nucleophilicity is reverse of the basicity order. Okay, so here you see CH3S minus and O minus. Okay, nucleophilic center is different.
right, belongs to the same group. So their nucleophilicity is reverse of their basic order. So if I write down the correct order of nucleophilicity, that will be maximum for ETO minus, then we have OH minus. After that, we'll have CH3S minus, and in the last, we have CH3O minus. Hence, option A is correct over here. Option 1. Is it clear? Nucleophilicity order is same as basicity. Okay, there's no difference into that. But one thing you have to keep in mind, when the nucleophilic center is different and they belong to the same order, then the order will be reversed. You can also compare these two like this. Oxygen with negative charge is more stable than sulfur with negative charge. Hence, the tendency for this to attack as a nucleophile will be lesser than this. Okay. Second thing is what? That since oxygen being more electronegative element, so it will attract the electron pair towards its side strongly than SCS3S minus, right? So here the attraction of this electron pair towards the oxygen will be more. Here it will be less, so it can attack easily. So it is a better nucleophile. Understood? Correct. So all these points that I have given you here, where you are making mistake, because you see, all of you said first option. So fourth and third is fine. You get confused with these two, since you did not know this particular rule. So all these rule you noted down so that you can revise it later on when the exam is there. Okay, like 1 or 2 or 4, 3, 4 days before the exam. Okay, so these kind of rules you just keep in mind. Okay, next question. Carbocation is least stable. Shreyas is getting C. Shreyas is getting C, all others are getting B. Okay, see the option. Okay, we have phenyl CH2. Okay, fine. You see here, first of all, this is vinyl carbocation, right? But the difference here it is what? Double bond in B. We have a double bond here. I think we have a double bond here. Atmesh. You see, this carbon atom is sp2 hybridized. This carbon atom is sp. I'm talking about the carbon atom which has the positive charge. Sp hybridized. This one is again sp2, and this is again sp2 hybridized. Okay, right. The question is which carbocation is least stable? That's the question, right? So we know more electronegative element, on that the negative charge is more stable, right? So if the question is anion, then the answer would be anything else. That depends on some other factor that we won't discuss now. But the point is the difference in hybridization is there. And option B, the carbon atom is the most electronegative. This one, since it is sp hybridized. So most electronegative element, positive charge on it is the least stable, right? Hence, answer will be option B. Correct? All of you are getting B only. So I'll move on. Tell me this one. Most stable carbocation. What is the answer? How it is D? Atmes, why it is option C? All of you are getting different answer. Okay, Atmes, not Shreyash. Why it is option C? Shreyash. Atmes is getting A. Why A, Atmes?
3-degree carbocation hyperconjugation. Hyperconjugation. 3-degree carbocation are most stable. Where is 3-degree carbocation we have, Sanjana? sp3 hybridized. Where we have more hyperconjugative structure in C. How many alpha hydrogen we have there in C? Option C. Where we have maximum number of alpha hydrogen? Yes. The maximum number of alpha hydrogen is present in A. Correct? So in option A, we have maximum number of hyperconjugative structure possible. And that's why option A is the most stable carbocation due to hyperconjugation. Is it clear?
Okay. So number of alpha hydrogen present here is 5. Here number of alpha hydrogen is 4. Number of alpha hydrogen, here it is 0. And the number of alpha hydrogen, here it is 3 plus 1, 4. Okay. So maximum number of alpha hydrogen present here. That's why maximum hyperconjugation and hence most stable. Understood? Next question you see. The compound which would give the most stable carbocation on dehydration. Okay, tell me. Most stable carbocation on dehydration. See, third option on dehydration, we are getting what? 3-degree carbocation. Yes, we'll get tertiary carbocation here, 3-degree carbocation on dehydration. Here we'll get 1 degree. And here we get again 1 degree. Right? Tertiary carbocation is most stable. So hence option C. Okay. Next. Following graph, the stability of different carbocation have been shown. Potential energy you have to match.
Okay, all of you are getting C. Why is it C? Why first one is the most stable? See, the simple thing is what the most stable carbocation will have the least potential energy, right? So graph C belongs to the most stable one and graph A belongs to the least stable one. Yeah, so the stability of carbocation, if you see in these three molecules, stability of carbocation that follows the order. First one is most stable. Then we have second one, and then we have the third one, least stable. Yeah, right. So stability order is this. Hence, the order of potential energy, more stable one, least potential energy, order will be reverse, right? So third one will have the least, then we have second one, we'll have the max, then we'll have second one, and then we'll have the first one. Okay. So the maximum potential energy for A, so third belongs to A, second belongs to B, and first belongs to C. So one is C, second is B, third is A. So option C is correct. Right? So all of you have got this. Next question you see. The decreasing order of basic characters of the following. What is the answer? Seventh one is A. Why is that A? The first thing, and from this only you can write down the answer for this question. This molecule is what? Pyrrole, right? We have a double bond here and double bond here, right? So for this molecule, the lone pair is delocalized, right? This lone pair is involved in resonance. So since it is involved in resonance, so its basicity is minimum. Minimum basicity. Why minimum? Because this is also it can donate this lone pair also. This also can donate lone pair of electron, and this also can donate because it is there in the p orbital which is perpendicular to the ring. It is not involved in resonance. This is pyridine, right? So in pyridine, the lone pair is not involved in resonance, but in pyrrole, the lone pair is involved in resonance. So hence, if we compare all these four, this one should have the minimum basic character. Okay, so second one is minimum, which is only there in the first option. So this one is right. Okay. Third one is see why this third one is maximum because both these nitrogen can donate lone pair of electron. Yeah, that's what I'm discussing. Both these nitrogen atom can donate lone pair of electron. If you compare this lone pair is involved in resonance with this ring, right? And here also it is there, it is involved in resonance. But whenever you draw the resonating structure here, one nitrogen atom will always have the lone pair on it. That's why this is slightly more basic than this. Understood? And how is 1 less because than 4? You see, this is pyridine, right? This is NH2. Actually, you see what happens if you compare these two. If you compare these two, this one will be more basic than this. Okay. And similarly, if you compare one and third also, third one is more basic than first because it simply has two nitrogen atom and both can, donate lone pair of electron. Both has this capability of donating lone pair of electron. But if we compare one and fourth one, right, here it is aniline and here it is pyridine. Okay, so this is again, since this lone pair is again there in the p orbital perpendicular to this, but this lone pair in aniline, you see this, and we have pyridine. This is the lone pair. So this lone pair is involved in resonance, correct? And this is not involved in resonance. So if you consider only this, so first one should be more basic than fourth. Okay, so first one should be more basic than fourth, and second one is list. They are not getting any option. Just a second. This is aniline and this is pyridine. So one pair and it comes over here. If this is involved in resonance, so obviously the basicity of the first one, third one should be maximum, and first one should be more to that of fourth one, and then we have the second one. I think this should be the order. These two we have to interchange. Okay, here it is involved in resonance and this is not involved in resonance. Why third one is maximum? Because we have two nitrogen atom which can donate lone pair of electron. Second one is minimum because it is involved in resonance. Okay, we'll see the next question. This one you tell me, arrange the following order of increasing acidic strength. I have done this kind of question also. X, Y, and Z. Tell me which one will have, what is the order of acidic strength? So on the other hand, Simon is getting A, Atmesh and Vishish is getting B. Why it is B, Atmesh and Vishish? See, I'll just tell you. First of all, the carboxylic acid is the most acidic here, right? So X would be maximum because of the carboxylic acid. We'll have maximum X. Now both are amino acid here, right? So the effect of this, which is plus R effect, minus R effect, electron withdrawing nature of this group. This group has electron withdrawing nature, right? Because of this group, the effect of electron withdrawing nature of this group is more over here than here, right? And hence the removal of H plus ion from this like part of this molecule is more easy, and hence the order should be X, Z, and then Y. Is it clear? Because of electron withdrawing nature of this group, the effect of this, however, we cannot say here that it shows minus R or plus R effect. But since this is the bond with which the key C double bond OH is attached, right? So you understand like this. Here we have NH3 plus NH3 plus. If you see, these two are electronegative elements. So all these bond pair of electron is shifted towards the oxygen atom. Carbon becomes slightly positive. And when this carbon becomes slightly positive, it will drag few electrons from this bond pair, right? And hence the effect of this group is more over here than this, and hence Z is more acidic than Y. Clear? Next question. The increasing order of pKb value of the following. A, B, B. Most of you are getting B. Okay. pKb value is inversely proportional to Kb, and hence it is inversely proportional to the basicity. So we have to find out the reverse order of basicity here. So which one is the most basic compound? CH. See, this carbon is 1,2 sp hybridized. This is hydrogen. This is NH2 minus and CH3. So if I find out the conjugate acid of this, that will be CH4, NH3, H2, and this is acetylene, right? So this is the, in all these, if you compare, this is the strongest base, right? This is the strongest base and least acidic. So its conjugate base, least acidic, so its conjugate base will be weak but strong base. Weak but strong base. So if you compare this, this is the most acidic compound we have. Correct? Since we have to find out the reverse of basicity order, basic order, then we are trying to find out which one is most acidic. That is nothing but the order of pKb. So whenever you have to find out the pKb order, you just find out the acidity order of this acidic order. That will be the reverse of basicity, right? So which one is the most acidic compound in all this? Can you tell me? Tell me the acidity order. Try once. What is the acidity order of these compounds? No? Okay. You see here, acidic order you have to find out. That will be, obviously, this NH2 minus will be more acidic than this first one. So what we can say, the third one, I'm comparing just one by one. Third one should be more than 1. Okay. Third one should be more than 1. And fourth is also second and third if you compare. Second and third, right? Hydrogen is not that much electronegative, right? So this second will also have the more acidity than the first and the third one, right? And if you compare the fourth one and the second one, obviously this fourth one will be more. Okay, just a second. This is the order we have. We can surely say that the basicity of this is more than is less than to NH2 minus. Basicity of pKb of NH2 is more than to that of this. Means third one, basicity of NH2 is more than this. The third one is pKb of NH2 is less than the first one. Oh yeah, just a second. I've done the wrong thing here. Just a second. This one is not right. Okay, we can easily say that the basicity of NH2 minus is more than this. So pKb of NH2 is less than. Okay, so third one should be less than the first one. Okay, third one should be less than the first one, and then the order will be reversed. I have given the reversed order over there. So first, third, second and fourth. If you compare second and fourth, which one will is more acidic? Second and fourth, can you tell me which one is more acidic? Second and fourth, you tell me. Fourth is more acidic than second. Fourth is more acidic than second. Okay. So second and fourth, yeah, right. So fourth is more acidic than second. Okay. So now you see, third one should be less than first, and fourth one should be greater than two. So if you compare this, fourth one greater than two, we are not getting any option here. Oh, there is something mistake. There he has given third and third here. Okay, I'll write down my answer. Okay, whatever I'm getting. The basicity of first one, pKb of first one is more than third. pKb of this is more than third. And second and fourth, second and fourth. So CH4. So this should be first, third, and then we have, I think, second will have then, and then we have the fourth one. Is there any option? I think third option we are getting. Yeah, it's the third one, I guess. You're saying fourth one is more acidic than second. Okay, we have to find out the basicity, right? pKb. So basis reverse of basicity means acidic order we have to find out. So acidic, which one is most acidic? Okay, you tell me what is the hybridization of carbon here? It is sp3, right? What is the hybridization of nitrogen here? sp2. Hybridization of this, let it be, and this carbon is sp hybridized. So you tell me one thing. Okay, you tell me one thing, that the conjugate acid of this, and this is the conjugate base of that acid. All these are conjugate base. If you add H plus all into this, right? So which one is most stable here? This one is most stable, the first one, because this carbon is sp hybridized. Okay, so this one is most stable, means the conjugate base, this is the conjugate base which is most stable. Then third and fourth, I'm comparing first, third and fourth. So this one is most stable, right? So acid gives, strong acid gives stable and weak conjugate base, right? So this one is stable, but it is weak conjugate base. Means if it is weak, so this should be more acidic. So if you compare the basicity or of first, third, and fourth, the order should be, it is for fourth one it is maximum, then we have third, and then we have first. Yeah, it's correct. Now I got it. Fourth one is maximum, third, and first. And H minus is obviously more acidic than these two, third one and the first one. So the answer will be, it is maximum for fourth, then one, and then third, and then first. So answer is this one is correct. Whatever I've done initially, this is not right. Understood this? See what I have done, that this H minus, the acidity of H minus is more than to this NH2 and this, the first one. Okay. And how we compare this first, third, and the fourth one, that we can do according to the, the stability of these bases, conjugate bases. Okay. If you see, we know this fact that strong acid gives you a stable but weak conjugate base. Okay. So this one is, if you see the stability, this one is most stable. The stability order will be maximum for this, and then this, right? According to this, if you compare, you'll get the order of basicity will be this, and then you can include second one into this, you'll get answer as this. So fourth one is the right answer. Got it? Yeah, you are also getting the same thing. Okay, next question you see. This one, resonating. I have discussed the Stability of resonating structure. Tell me this one. There are 7, 8 rules if you remember. Tell me quick. Tenth one is A.
Reason? Tell me the reason. Charge separation you have to check. See, the difference in these two is what? We have, okay, I'll write down the charge. Maybe it is not visible. See, this is positive, this is negative, positive, negative, negative, positive, positive, negative. Charge separation you have to check. See, what you can say that whenever the like charges present adjacent to each other, like charges present adjacent to each other, then stability decreases. Okay, so if you see here, all the molecule, if you see where we have charge present at adjacent atom, 1 2 3 4, see continuous charges are present. Here also we have the same thing, and compared to these two, here the charge separation is there, but here the charge separation is large, here it is less, means charges are placed very close to each other, right? So obviously if you compare all these four, these two must be less stable than these two, right? Charge separation we are considering. But in these two also, you see we have positive negative charge present adjacent to each other, and here we have positive positive charge present adjacent to each other. So like charges will decrease the stability, hence the first one is the least stable compound. Option A is correct. Got it? Yeah, right. Yeah, next question you see. The correct order of stability of the following species. Eleventh one, Vishish is getting D. D is right. Why, you see? First of all, in this example, you see, we have hyperconjugation as well as resonance. Since all these are positive charge, okay, and this is the lone pair of electron. So we have 3 plus 3, 6 alpha hydrogen and resonance. Okay, here we don't have oxygen present here, right? So we have only 3 alpha hydrogen and 2 alpha hydrogen here. But here we have 3 alpha hydrogen plus resonance. So first, in the first compound, you see what all things we have. We have 6 alpha hydrogen and resonance possible, right? The second one, we have only 3 alpha hydrogen. Third one, we have 3 alpha hydrogen and resonance again possible. Fourth one, we have 2 alpha hydrogen. See, alpha hydrogen means what? We can have hyperconjugation possible. Alpha hydrogen means hyperconjugation possible. More number of alpha hydrogen, more will be the hyperconjugative structure, right? So in the first one, we have maximum hyperconjugation. Third one, we have resonance also there. Third one, we have resonance also there, but number of hyperconjugative structure is lesser than the first one. So first is obviously most stable. Then we have third one. Why third? Because with alpha hydrogen we have resonance also. But in these two, third and second and fourth, if you compare, second one will have more hyperconjugative structure possible. So we have two, and then the last one is fourth. Hence, option D is right. Correct. 23rd. Which of the following molecules in pure form unstable at room temperature? Why it is D? See, this compound, the third one, this is a conjugated system, contains only 4 pi electron. right? So it is anti-aromatic, and hence it is unstable. We have 4 pi electron here also, but it is not a conjugated system. That's why this is not anti-aromatic. Okay, so answer will be option B. That's what 4 pi electron it has, but it is not a conjugated system. That's why it is not anti-aromatic. Got it? Next question. The hyperconjugative stabilities of tertiary butyl cation and 2-butane respectively are due to. See, you can do this question like this. Tertiary butyl cation means CH3, CH3 and CH3. This is tertiary butyl cation, so positive charge we have here. Now this positive charge means what? We have a vacant p orbital here, empty p orbital, right? Which usually forms a sigma bond, but since it is empty now, so what we can say, sigma p empty, right? And there is only one option, empty sigma p. Then they have written 2-butane. I don't think it's 2-butane. It should be 2-butene, I guess. There is some mistake. Okay, let it be. I'll cross check this question. Okay, this should be 2-butene, I guess. But I have to cross check. Okay, so let it be this question now. But with this data, we can understand that in tertiary butyl cation, we have sigma p empty orbital, right? P empty orbital and empty p orbital we have there, which forms a sigma bond. So according to this information, we have only one option possible. That is option A. In these two, you see it is filled. Sigma sigma star is not there, right? So according to this, option A should be there, but this is something missing over here. It should be 2-butene, I guess, but I'll cross check this question. Okay, so let it be this question now. I'll give you the another one. You do this one. Which of the following molecules with significant dipole moment? Yeah, we have done this in isomerism, right? That OH bond may be like this, or another possible is this OH and OH. So in this case, mu is equals to 0. In this case, mu does not equals to 0 because of the orientation of this bond, right? So whether we have O or S, we have the same logic. For C and D, we'll definitely have dipole moment. So option B is correct. The logic is what here? For zero dipole moment, we must have linear molecule present here, like this cyanide group. Okay, monoatomic or linear molecule present. Right? We have discussed this in isomerism, if you remember. Which of the following statements is wrong? Now it is alkane. B. Agnes is getting B. Okay. So some of you are saying B and some of you are saying D. See, first of all, heat of combustion, two things you understand. Okay. If for larger molecule, larger cycloalkane, I'll write down. For larger cycloalkane, the heat of combustion is more. So basically we say what? Heat of combustion per CS2 molecule increases, like this one, right? So this one is also right and this one is also right. Right, if you see these two options, if you do not know anything in this question, you see this option A and C, both are same actually. So if this one is wrong, so this should also be wrong. And since it is the only one correct answer we have, so both cannot be wrong. Right, so this is how you can eliminate option A and C. You understand my point? Both are actually the same thing. The logic is same to these two options. If this is wrong, this should also be wrong. But both cannot be wrong at the same time because the option has only one answer, right? So hence A and C you can eliminate. Okay, now cycloalkanes, the planarity of that, if you see in cycloalkane, except cyclopropane, this you must remember, except cyclopropane, cyclopropane, cycloalkanes are non-planar. Generally higher cycloalkanes are non-planar, right? But cyclopropane is planar. Okay, this you must remember. This is again one information I am giving you. Cyclopropane is planar and all other cycloalkanes are non-planar. Generally higher cycloalkanes are non-planar only. So we cannot say cycloalkanes are planar. So this is the right answer for this question, right? It is not true for cyclopropane, which is given here also, you see. Right, that's why if you remember cyclohexane, the structure is this. Oh sorry, the structure is this, cyclohexane, chair form, right? And it is not a planar structure. Okay, so generally higher cycloalkanes are non-planar. Cyclopropane is planar in nature. Okay, so option B is right. Got it? This one, both alkane and alkene. Tell me fast. What is the answer? Cobb reaction. Yeah, it's correct. The correct answer is this. This Kolb reaction actually it is used for the preparation of alkane, alkene and alkyne. Okay, it is used for the preparation of alkane, alkene and alkyne. Williamson synthesis is used for the preparation of ether, if you remember. Wood's reaction, generally we get higher alkanes, symmetrical alkanes into it. Okay, Sandmeyer reaction is used for the preparation of diazo compounds. Diazo compounds. That's why the answer is Kolb reaction. It is the Kolb electrolysis actually. Okay, it may give salicylic acid also depending on the reagent that you are taking, but there is a method we call it as Kolb electrolysis. It is actually referring this reaction, Kolb electrolysis method. There we take the salt of sodium or potassium salt of acid, which gives alkane or alkene or alkyne. That one salicylic acid is Kolb Schmidt method probably. Okay, it is Kolb electrolysis. Right, so answer will be option B. Tell me, the structure of the compound with molecular formula this that has only 2-degree hydrogen atom. You have to draw all these structure. Tell me, what is the answer? Wood's reaction Saundarya, it gives alkane, generally alkane, correct? And that alkane will be symmetrical alkane. See, actually, Wood's reaction, see in Wood's reaction, generally we take Rx plus 2Na plus XR. This alkyl group will generally take same alkyl group here, right? And that gives higher alkane, RR plus 2NaX. If you take R dash here, then we'll get mixture of alkane. R dash we also get, R dash we also get. I mean these three mixture of compounds will get. We'll not get alkene into that. Right? So if you take different alkyl halide, you'll get mixture of alkanes. But if you take same alkyl halide, you'll get only one alkane. Right? Higher alkane. Generally, Wood's reaction we use for the preparation of symmetrical alkanes, higher alkanes. Okay. Yeah, if R has a double bond here, then you'll get alkene also over there. Right, depends on what you are taking. But generally, Wood's reaction, we never see this reaction for the preparation of alkene. We see this reaction for the preparation of alkanes always. So if it is not mentioned, we consume this as a preparation of alkane itself, not alkene. This R can be anything. You can take CH2, double bond CH3X. This you can take. Right? In that case, you will get alkene. Right? But that will be alkene only, not alkane. Understood? This plus 2Na plus XCH3. These two are different first of all. Then you may get mixture of alkane and alkene. But generally, Wood's reaction, we don't take different alkyl halide. That is why we are not considering this as an answer. If the question is multiple choice, more than one correct, then we'll take B and C both in that case. Right? Tell me, what is the answer for 17th one? By looking at the option, you can say what is the answer, and this is very basic. Yeah, 17th is B because cyclohexane. All carbon atom is sp2 hybridized. This is cyclohexane. All carbon atom is sp2 hybridized, contains only secondary hydrogen. So option B is correct. You can also draw the structure of other molecules. You can understand. Okay, if you want, you can draw, but I don't think it's required. Very basic thing. You can draw the structure and you can write down the answer. Next one is C, 29th. What is the answer? See, first of all, we have COOH. So you will get here the salt of this COO minus, COO minus, and K plus, salt of this, right? When you do the electrolysis of this, electrolysis here, right? Then oxidation takes place at anode, and you'll get two different product here. One is this, we have a double bond, and the other one is this, we have a double bond here, right? So these two are actually cis and trans isomers. So we'll get here geometrical isomers. Okay, K2CO3 goes out, and then at anode oxidation also takes place and forms double bond here, and that will be the geometrical isomers. Is it clear? First of all, with this solution acid, you'll get a salt of it, and when the electrolysis takes place, K2CO3 goes out. Okay, oxidation takes place, and we'll get a double bond, and that will be the mixture of uh, two isomers, that is cis and trans we get.
One more thing you think here, since it is only one option is correct here, when you look at this, you can easily eliminate option B. Enantiomer is not possible into this. Right, enantiomer is not possible. This you can eliminate easily. Now the positional isomer is nothing but the structural isomers also. So position comes under structural isomers. So if this is correct, this should also be correct. Right? So you can also eliminate these two options accordingly. Like this if you think. Once you know if the answer has only one correct choice, then enantiomer you can opt in eliminate because it does not form an enantiomer. However, it is a, you know, what we can say, we are guessing it simply, but by looking at the molecule you will have this idea it will never show any optical activity, so enantiomer is not possible into this. And positional structure, since both are, position comes under structure only, so we can eliminate these two options also. Hence option A will be the more appropriate choice we have here. If you do not know this, then like this you can eliminate few options. Okay, next question you see. Question number 30. Which of the following reactants is suitable for the preparation of methane and ethane by using one step only? One step reaction you have to write down. Nineteenth one is C. What are the method we can use for this? Okay, C is correct. You can obtain alkane from this. So what are the possible method we have with this? Preparation of alkane from alkyl halide. Wurtz reaction we can use, and we can also use reduction method in presence of zinc with acid. If you have Rx and Wurtz reaction gives you RR, and here we'll get RH, right? Which of the following reactants is stable for the preparation of methane and ethane? Yeah, we'll not get methane from Wurtz reaction, but we can get what? We can get this methane and ethane here from this reduction method. So Wurtz reaction gives you higher alkane, right? So we will not get methane over here, but here we'll get the both thing, right? So in this reaction, okay, answer is C, alkyl halide.
highest boiling point. Highest boiling point is expected for. This question is asked in JEE. N octane, correct. Normal, as branching increases, boiling point decreases. Okay. As branching increases, boiling point decreases. So all molecule you see, they have equal only 8 carbon atom, all these molecule, except this N-butane, right? So obviously uh, as the molecular formula, molecular mass increases, boiling point increases, and when branching increases, boiling point decreases. So with these two logic, option B is correct, N octane. Okay. Next, this one. Okay. You see, first of all, this is an alkyne. Okay. And cyclopropane. Cyclopropane is highly unstable. This is highly unstable because of angle strain, high angle strain, right? So with H2 and platinum, this will completely hydrogenated. This will get the hydrogenation takes place here completely, and it converts into octane, that is normal octane. Why octane? Because we have 3 3 plus 2 carbon here, we have total 8 carbon. So with H2 and PT, complete hydrogenation takes place. Must remember this, complete hydrogenation with H2 and PT, and this converts into N octane, normal octane. So answer could be anything, B, C, or D, anything between these two. Okay. Now here we have H2 with P2 catalyst. Okay. This actually hydrogenation takes place, but this will reduce this triple bond into double bond, right? Triple into double bond, and we'll get cis form over here. Cis form will get over here, but complete hydrogenation does not takes place here. only one pair of hydrogen atom will attach onto this carbon atom. So this triple bond converts into double bond, and the answer will be this option D. So basically, this P2 catalyst does not give complete hydrogenation. Okay, and it converts triple bond into double bond. Option D is correct. Okay, these two reactions you must remember, especially this P2 catalyst. Understood? Next question. This one. Do this is the last question for today. Easy one. Try this. Done. Is it C? Saime is getting C. Others, tell me. What is the last step reaction, Saime? That is from D to E. What is that reaction called? Okay. You see this, I'll rule this one. First of all, the first reaction is what? It is Wood's reaction, right? Na ether. So the product we get here is this. Okay. The first step, it is B. Now, in this, if you do the chlorination of this one, 2 moles of this chlorination with H nu, See, this halogenation of alkane is always syn addition. Okay, must remember this. The two chlorine atom attached from the same side, Cl and Cl. Halogenation of alkane is always syn addition. Why it is syn? I'll just tell you one intermediate product here. The intermediate product, you'll get a cyclic halogenium ion here. Cyclic halogenium ion will be like this. Suppose we have X here, X, and this is like positive charge. This is a cyclic halogenium ion we get. Okay. Okay, fine, fine. So it's not syn, it is trans addition actually. Sorry. Because of this uh, cyclic ion, what happens? The other halogenated ion or halide ion attacks from the opposite side, and this bond breaks like this. Okay, and then halogen attach like this from this side and this side like this. So whatever it is, this is not a 3D representation. Just we have one thing here, that two chlorine atom attached at this position. You can draw this chlorine atom this side also. That would be actually better. This chlorine here and this chlorine here, because it is a trans addition, not anti addition, not syn addition. Okay, so we'll get dichlorinated product here. Now in this, what happens next thing, when you are adding alcoholic KOH, so at 2 moles of alcoholic KOH, we know it gives what? It gives alkene, right? So double bond will get here, double bond will get here. So we'll get this as the product here. Plus 2 KCl goes out. Okay. Now the last step we have what? That this reacts with ethene, CH2 double bond CH2. Now this reaction is what? This reaction is, we call it as Diols Alder reaction. Now this C double bond C, we can also write it as this. This is C double bond C. Now what happens here? This pi electron attacks onto this carbon. This pi electron goes here, and this pi electron comes onto this carbon. And finally, this carbon and this carbon joins. So we have a double bond here with 2 methyl group and 1, 2, 3, 4 a ring like this. So the product we get here is this. This is 2 methyl group and we have a double bond here. This is the answer. We have option C. Last step reaction where we have this. Let me draw this. You have a compound which has 4 carbon atom, conjugated compound, 4 carbon atom, plus a compound has 2 carbon atom double bond. This reaction is Diols-Alder reaction. And in this, like I discussed over here, this pi electron jumps over here, this pi electron comes over here, and this comes over here. And finally, since this is positive, this is negative, these two also joins. So we get a ring structure over here, and the final compound is this. The name is Diols-Alder reaction. Did you understand this? Halogenation of alkane. You must go through halogenation of alkane. Alkene if you have, correct. Alkene if you have, that gives you trans addition of halogen. Okay, we'll discuss this later on also in the next class. Clear, understood? Okay, so we'll see you in the next class. This is almost done. I think 3-4 questions are left. We'll probably solve that also in the next class. And then we'll solve some other chapters. Right? Okay, thank you all for joining. See you soon. Bye.